Hi, welcome to another edition of Linear Algebra. Today we are going to start the section on the inverse of a matrix. Let's go ahead and visit this topic together. So, you remember from elementary school, of course, that if you have a number, then you had the inverse of that number. However, you multiply the two of them, you get 1. The only exception there was 0. For 0, we could not arrange this. There was no inverse of a 0. You typically say do not divide by 0. Now, given a square matrix A, how do we find another matrix? Let's call it A prime, so that the product, whichever way we do it, will be the identity. So we are going to investigate this topic in a couple of lectures. So today we are going to go ahead and talk about, well, how do we actually find this thing? When does it exist? When is it that it would not exist? And some of the properties of it. So again, remember our long-term plan for this course was to do the entire field of mathematics we know so far from elementary school to calculus 1 and do it all for matrices. So long ago we said we want to duplicate everything we know: addition, subtraction, multiplication, division, power, and functions apply to a matrix. We added a new creature in the middle, and that was transpose. We have that in the mix as well. So far we have talked about these 4 operations. Addition, subtraction were standard operation, nothing surprising there. Just that your matrices had to be exact same size. Transpose was easy too, just turning rows to columns and vice versa. Then multiplication took us a while. We have to get used to that. It's a new thing. We said we have a pile of dot products to do, substantially more complicated than the multiplication we learned in high school. Now we are coming to division. Let's go ahead start this with some examples, see what is it we are talking about. Suppose I have a matrix M, and let's choose a friendly matrix, say 2, 3, 4. It has to be square. We're not going to talk about inverse of a non-square matrix for simple reason that this multiplication would not work. Okay, so we are trying to find a secondary matrix. We don't know what it is. Let's just give it a name M prime. We don't know what is in M prime. Let's just call it X, Y, Z, T. We want to arrange these 4 numbers such that M prime or M prime M becomes the identity, which in this case will be 2 by 2 identity. Well, how do we do that? Well, amazingly enough, we already know we have the tools for doing this. So how do we do this? Well, I write this times that equal to that. You get a bunch of equations. Just go ahead and solve those equations. So I have 1, 2, 3, 4. I want to multiply this thing with X, Y, Z, T, and I expect to get 1, 0, 0, 1. From this equation we want to find X, Y, Z, T. Once we do that, well, we have our inverse. We have this M prime and call it a day. So how do we proceed here? Of course, just as before, we go ahead, pick the rows of this, columns of that, multiply these with those, and we expect to get that. Second time around, you multiply with this, and you expect to get that one. Let's go write it out. So yellow times the blue, what do I have? 1 times X plus 2 times Z has to be this corresponding entry on the other side. 3 times x plus 4 times z has to be the entry here, that is 0. Well, this is an ordinary 2 by 2 equation. We can go ahead and solve it and find our x and z. In same fashion, we go ahead and do the green one, that is, I say 1 times y plus 2 times t has to be the green entry on this side is 0, and 3 times y plus 4 times t has to be the entry here. So I have to solve this, and I have to solve that one. Well, we always try to find a shortcut so that these kind of activities can be done faster and perhaps save a bit of time. We look at this thing and see the left hand side of this and that are exactly the same thing. Not a big surprise because they are both these yellow matrix here. The right hand side are the columns of this identity separated into different vectors. So I think about the following. I have to do elimination here to find x and z. Well, I'll be doing exactly same elimination here to find y and t. The only thing different between these two is the right hand side. So perhaps I can recycle my effort, just like you recycle your used bottles and plastics and such, hopefully. In computations also, we always think about recycling something because, well, computations cost time either from you or cost expenses on a computer and such. Imagine you have large matrices and then you have to actually pay. You have to pay certain company to give you a computer to actually solve these things. So there's an issue of cost as well. But right now what we have in mind is a systematic way of going after this that can be used for bigger matrices as well, and we can do it quickly. So if you were to do this thing by Gaussian elimination, what would you do? You take these numbers and then you have the right hand side, which is 1 0, and then you go ahead, go through some steps, you reduce this, and then your whatever is on the right hand side, it's going to be exactly your solution. So if I go ahead and perform the Gaussian elimination on this thing, I'm going to get my x and z. Well, when you are doing y and t on the left hand side, you have the exact same matrix that you had over there. It's just the right hand side is different. So we think about this smart shortcut. We say, okay, let's do these two at the same time. So whatever I do here, I also do it here, and I don't write it second time. I don't do the calculation second time. I do all of it at the same time. So here's a trick. You say 1, 2, 3, 4. Put these right hand sides in order here. 1, 0, 0, 1. All right, 1 0 0 1. So by now what do I have? The original matrix that I want to find its inverse is sitting here, and then the right hand side of this equations is just identity matrix. Now what were you going to do to either of these things? You would be applying the Gauss-Jordan operation until you get your reduced row echelon form, which in this case has to be identity. So we are going to apply the Gauss-Jordan elimination steps until the left hand side becomes the identity, and then what we have on the right hand side would be exactly our holy grail here that we are after. So by the time this becomes identity, if we manage to get there, what is going to show up here is going to be the inverse that we are going to utilize. So that's our procedure for doing inverse of a matrix. So in short, we start with the matrix and then attach an identity to it. Apply Gauss-Jordan elimination to this. Well, apply the same thing to the right hand side as well. In the process, if you manage to bring this thing to identity, what shows up on the right hand side would be inverse of that. Okay, again, you have the option of doing this thing by hand, and I encourage you to do this thing by hand for smaller matrices. But by the time you come to 4x4 and such, it's going to be a real chore to go through all these steps. Quite a bit of number of arithmetics has to be done, and well, we are not all that interested in doing that. So here is a shortcut that helps us with the arithmetic. We have to know the Gauss-Jordan method, but now here's, I go click on the edit. Now remember, if you have a matrix that is let's go back here. Sorry, what happened? Not sure what happened. Okay, sorry again. So the matrix that you're making is gonna have twice as many columns as the original matrix you had. So this was 2x2, and this thing is gonna be 2x4. So you make room for the 2x4. Left side is gonna be filled in with the original matrix. Right side is going to be filled with identity. So let's go ahead and do that. So we are going to, let me find my way back here. Okay, so I have, we said it was 2x2, it becomes 2x4. Okay, 2x4. And then my matrix was 1, tab 2. Here comes the identity. I just put 1 and 0. Here I had 3 and 4. Right hand side, I make identity. So you see that here I have my 1, 2, 3, 4. Here I have identity 1, 0, 0, 1. Okay, we are right here. Oh, what do? We just take aim at this 2x2 and go after reducing it to the identity. That's we are making the row reduced echelon form. So here, this is the pivot, this is the target. So we are adding minus 3 times row 1 to row 2 to make this thing go away. Make this thing identity. So divide this by minus 2. Notice the right hand side got divided. Now use this as a pivot and eliminate this one. That was the Jordan step. So now you see, by now we got an identity here, and on the right hand side I have this particular matrix that showed up. Let me write it down so that when I want to sorry, when I want to write it here, go on my, so we go through a certain number of steps here. What came out of those, so that was our Gauss-Jordan elimination step. I got 1, 0, 0, 1. That was my identity. On the right hand side, I came by minus 2, 1, 3 halves, and minus 1 half. Again, if you had solved this problem, find the x and z here, you would have gotten minus 2, 3 halves. If you had solved this problem, you would have obtained 1 minus a half. But instead of treating them at 2 separate rounds and going to that software or doing by hands two times, we are just economizing and doing all of it at the same time, and it looks much nicer, and outcomes are inverse. So here's my inverse. Now again, what does it mean to have an inverse? It means the following: if I have the original and what I claim to be the inverse, minus 2, 1, 3 halves, minus a half, what I get is that if I take this, multiply by that, What do I expect to get here? I expect to get identity. Let's see if it actually, so this is my M. This is what we claim to be its inverse. So I wrote it M inverse, that is same as the M prime that we are starting with. So I went a little bit ahead of myself. This is, we are going to write it as M inverse as opposed to M prime. So 1 times minus 2, that's minus 2. 2 times 3/2 is 3. Add them together and you get 1. 1 times 1, 2 times minus a half, 1 minus 1 is 0. 3/4 times this becomes minus 6 plus 6, I get 0. 3 minus 2, that gives me 1. That is my identity. And if I do it the other way, same thing happens. If you try minus 2, 1, 3/2 minus a half is the first matrix, then 1, 2, 3, 4 as the second matrix. This is one of those very few cases in linear algebra that you do get commutativity. Like, if it doesn't matter if you take M inverse multiplied by M or M times M inverse, again minus 2 times 1, 1 times 3, I get 1. 4 and minus 4, 0. 3/2 minus 3/2, 0. 3 minus 2 is 1, and I get identity. So that's the process. Again, for small matrices, it's easy to do by hand. As the matrix size increases, the number of steps grows, and it grows pretty fast. It goes with the size of cube of the matrix that you have. That is, like if you compare a 10 by 10 versus a 100 by 100, the 100 by 100 is going to cost 1,000 times more effort to figure out its inverse and so on. So it's proportional to the cube of the size of your matrix. Okay, that's something you're going to see in more advanced linear algebra classes. So, several things we want to mention about the properties of this inverse we just explained, and circumstances in which inverse might not exist. So, very important issue is that sometimes M inverse might not exist. So that's your favorite does not exist situation. Under what circumstances this happens? First of all, we do expect this, because obviously on a 1 by 1 matrix, if you want to call it a matrix, or for a number 0, you don't have an inverse. You were told since you were born, don't divide by 0. So we expect that matrices will show us same challenge. But the challenge is much bigger than that. Of course, 0, 0, 0, 0 inverse does not exist. Okay, we are not in doubt about that one. But it's not just the presence of zeros that causes this problem. If I had 1, 1, 2, 2, this looks like perfectly nice matrix. But this one also, the inverse does not exist. As the size of the matrix increases, it becomes actually a tricky thing to figure out if its inverse exists or not. And this is going to be an issue that we are going to be dealing with pretty much every day for the rest of the semester. So what happens here? Let's just go ahead and practice, see what goes wrong. So let's go reset this, maybe clear this thing, so what was it? Well, I have to do edit, 1, 1, this was 1, this was 1, this is 2, 2, and then identity. Okay, resume. I want to make identity on the left, and the right will be the inverse. Would that work? Well, I go ahead, eliminate, I get too much of a good thing. This guy got eliminated also, so I cannot convert it to identity. I cannot convert this thing into 1. I cannot use this thing to eliminate that entry either, and the process gets stuck. That matrix that we have does not have an inverse the way we want it. So in general, when is it that the process breaks down and we have situation where there is no inverse? If you have a matrix and you perform this Gaussian elimination, you make this into a 1, and then say you succeed in making the bottom ones into 0. Perhaps you get lucky on the next one also, and then items underneath that become 0. You go say to the next entry, if this one becomes 0, of course you cannot use 0 as a pivot. If you have some entries down here that are non-zero, well, you can swap them out and proceed. But what if all of these things become 0? What if these are all zeros and the entry on the diagonal is also 0? So if any step of Gaussian elimination, you come to a situation where the pivot is 0, what you want to use as a pivot is 0, and the entire sub-column also 0. Entire sub-column also 0. That is the recipe for disaster, or recipe for M inverse does not exist. We cannot proceed to make this thing into an identity. It means for that particular matrix, this system that you want to solve, at least one of them cannot be solved, and the process just stops. So sometimes N inverse does not exist. Well, then that means we better have a flag that separates one group from the other. So we say if M inverse exists, we say M is invertible. Okay, M is invertible. That's a word you want to get used to, and it's going to be there constantly in a variety of problems that we're going to look at. Problems start with assume matrix M is invertible, and so on, and the rest of the story continues. So that is something. So in this case, we say M is not invertible. There will be several other synonyms for this situation, for this kind of flag later on, but right now that should be enough for us. Okay, suppose two students work on such a problem. Is it possible for one student to find one answer, another student find another answer? Is there such a thing? No, it's rather easy to show that if M is invertible, then M inverse is unique. If M is invertible, meaning if somebody correctly finds M inverse, then anybody else who tries it, regardless of what kind of step the other person uses, then M inverse is unique, meaning everybody is going to come to the same conclusion as to what the inverse is, regardless of what steps they went through. Okay, so that's something I'll let you read about this one in the text. Next property that we come across this thing, sometimes you want to solve an equation, like you have M times X is equal to something on the right hand side. So how do we solve this? So from now on, anytime I'm going to write a matrix M. I'm going to assume M is invertible without mentioning every time. If M is invertible, solve an equation like this. Well, what's the trick? We're going to apply both sides with M inverse. The only difference between this and what you had in, say, Algebra 1 5 years ago is that you have to be careful how you write this thing. So let me write this equation: mx is equal to b. If you multiply on this side with the inverse, on the other side the inverse has to sit on the same location that you put it on the left. So if on the left you were on the left, on the right you're also on the left. Sounds a little bit silly, but that's M inverse has to be on the same location, meaning you couldn't put this thing on the right side of that because we said we don't have commutativity in general. Now why would you do that? Because M inverse times M, if these are inverses, this is just identity. Identity times X is M inverse B. So identity times anything is just that thing. And you get X is equal to that. So now we want to be immediate in these steps. If mx is equal to b, then x is equal to m inverse b. Okay, so let's bring up an issue that we have been saying over and over again, that once we came to matrices, we did lose certain things. One of the biggest losses was the loss of commutativity. That is, you cannot make a mistake of writing this as Bm inverse. There is no guarantee that such a thing would even exist, or even if it did exist, that it would be same as that. This is not same as this. One reason that the division notation is not used in majority of text is that if you write B over M, it's not clear which one of these things do you mean. Is it division on the left or division on the right? So some software, most notable among them is MATLAB, they have a compromise. They do two kind of divisions, like this type and then this type. So this is something that you see in a very respectable software out there, MATLAB, but it's not used in textbooks, so we are not going to use that. And this one, well, I saw it in one of the calculators. I showed it to you a couple of weeks ago, but again, it's not standard. So we are not going to write division like this at all. These things we are going to postpone it to whenever you take your MATLAB classes. And here we just emphasize, in general, we don't have commutativity, so you have to be careful. Where do you put that inverse thing? Okay, maybe just to emphasize this issue, I take one of the type of problems that's going to show up in your homeworks is solve the following. Okay, this is kind of a problem that reminds you of things maybe you have seen in well, the way this problem, let me write it just the way it shows up in your solve. I had already gone through a step of it. So we want to solve A inverse bx in parentheses to power of -1. On the right hand side is A inverse b cubed, the whole thing in parentheses, squared. Solve, well, there's so many things here, a, b, and x. What do you want me to find? Solve for x. Find x in terms of everything else, in terms of a and b. And typically these problems you can write the answer in many different ways. Let's specify type of the way to write the answer. Most often than not, the WebAssign will accept equivalent forms, but just to have a specific form. So in terms of products of powers of A and B. Okay, how do we proceed here? One of the crucial things is how do we handle the inverse of a product of two matrices? How's that going to go? Let me explain what the rule is, and then we are going to use it. Here is another surprise of matrices. If you have a matrix times another one, and you want to find the inverse of it, situation is going to be a bit different from what you had in like college algebra or algebra 1. Over there you would have said what? Over there you say if I have a times b to power of -1 or to any power, it's the first one to that power, second one to that power. That's good in ordinary algebra class, ordinary algebra, that was fine. What is different here is that the matrices show up on the right hand side in reverse order. So let me put this thing in a red box. Sorry. You remember something like this thing last time? Do you remember? Let me pause this thing and ask you, what was the situation we had seen that was very similar to this in the previous lecture? Anybody? So that was, of course, the issue of transpose. Transpose was the same surprise, that not only we transpose the components, but it shows up in reverse order. So we had that. We have for the inverse, and a couple of other things in linear algebra that we might come to it later on. Same thing happens, that sock and shoe principle that we talked about before, that when you're putting them on, you put the socks first and then your shoes. When you take them off, the shoes come off first and then socks. Same thing here. Now I want you to go ahead and perhaps investigate this thing and find out why that is. The way you do that is to take the right hand side, multiply it by mn to see if you actually get, if you are claiming this to be inverse of that, then if you take this, multiply by that, you do get the identity. Well, do you? Well, yes. You see how they are arranged? M and M inverse sit next to each other. If you had written the way you are used to in algebra 1, if you had M inverse, N inverse, and then you multiply it by Mn, these two do not cancel each other, nor do they play hopscotch. You cannot exchange it. But when M and M inverse are next to each other, the product is identity. Then identity times anything is just that thing, and then you have N times N inverse. That's going to be again another identity, and then you are done. Now, so this thing is the inverse of that. We have to keep that in mind in this problem. Now, how do I proceed? First of all, let's open everything up. This becomes A inverse. Now we said when you want to write the inverse of that, this is X inverse B inverse. Right hand side, you can leave this thing alone, or here we made a requirement that everything written in terms of powers. Again, a difference between the situation that we have now and what you had in high school. Over there, if you have AB squared, it was fine for you to write A squared B squared. That is gone right now, because if I have N times M squared, well, what is that? Is NM times NM. Now you want to write without writing parentheses, that's fine. The thing is that these two do not exchange their place. You cannot play the hopscotch with the matrices. So you cannot write this thing as n squared m squared. Then what can you do? Well, really, you cannot do anything. You want to square this thing? All you can do is write a inverse b cubed, and then again a inverse b cubed. Okay, so the inverse was written, if you want to write it, spell it out. There is no shortcut to it. You have to leave it like that. Okay, now we have to gradually clean this up until we get the x alone. So I have to isolate the x. Everybody else gotta go, and this has to be an x, not x inverse. So let's do this thing step by step. We get rid of a inverse. How do you get rid of anything? Multiply by the inverse of it. Inverse of a inverse, so here's another rule that we are going to use. Inverse of the inverse is the original matrix. That's easily believable. So if I multiply by a, you can just say I'm multiplying by a on both sides. So what does that do? This, when you multiply it by the inverse of your matrix, you have identity. So by now you're left, so this is identity. By now you're left with a x inverse, b inverse. These two happen to be an identity too. Identity times anything is that thing, so I don't need to write the identity b cubed, a inverse b cubed. Now we said we want to trim all the fat off and just have an x. Next I have to get rid of b inverse, so I multiplied by b. Notice where I put my b. I cannot put it on the left. I mean, you could put it, but it's useless because I want to cancel this b, and this b has to be on the right. If it's on the right here, on the left, it has to be right on the right as well. So what does that do? So this becomes the identity, this becomes x inverse, and this is just identity. You remember from last time that we said if you have powers of the same matrix, thankfully this rule from high school algebra is still there. Product of powers of the same base, you add up the exponents. So in short, you write this thing as b to power of 4. What else? Well, I want x. This is x inverse. What should I do? You take the inverse of both sides. So now you have b cubed, a inverse b to the 4 inverse. Now inverse of a inverse, as we said before, it's just inverse of a inverse is just the original matrix. And then you are finding the inverse of a product is a product of inverses in reverse order. So it becomes b to power of 4. That has to be written with an inverse. Then the middle one inverse. Then the first one comes last. Now we are going to have one more rule that says if you have b to some power and then you find the inverse of it, the answer is actually same as if you have the inverse and then raise it to that power. And for that reason we create a new notation and define what the matrix to a negative exponent is going to mean. So far we didn't have such a thing, but now we are creating that symbol from high school algebra. We have it here as well. We can condense all of these things. So if I have b 4 to power of minus 1, which is inverse of b4, it is same as the inverse to power of 4. This has to be established actually. And we create a new notation and say, okay, let's clean this up. We write b to power of minus 4, and by that we mean either of these two things. So I can clean up the answer here and write b to power of minus 4. Inverse of inverse is just a matrix, and this is b minus 3. So that is the answer in this case, and you're going to have several problems like this in your homework. So let's go ahead, write down the rules that we encountered in this problem and have them all in one place. What is legitimate and what isn't. So first of all, one thing we saw that is that the inverse of the inverse is the original matrix. So that's not a big surprise. Then inverse raised to a positive exponent like 2, 3 and so on. This is same as, so you can raise to that exponent and then find the inverse of that, and due to the fact that these are the same thing, we come and define what a negative exponent means. Negative exponent means either of these two, whatever you want. A big surprise, this is perhaps the only thing that's going to give you a pause among all of these things, is that inverse of a product is a product of inverses but in reverse order. That's a big issue. There is a tiny bit of interplay with the transpose as well. If you have a matrix and then you find its transpose and then you find its inverse, you get the same thing that if you get the inverse first and then apply the transpose. So the rules that we had the previous time, you can combine it with this set of rules here. And then what if I have a number, let's write the number A times a matrix, and then I want to find the inverse of it, like double of a matrix, find the inverse. You can find the inverse of your number just like you would find it in high school, and then inverse of your matrix. So this rule is still there, resembles the stuff that we had in high school. One thing, you don't want to go overboard. We don't have such a thing. We don't have, for example, AB squared is not A squared B squared. One of the big losses that we have because of what? Because of lack of commutativity. AB squared by definition means AB times AB. So I want to clean this up. But there isn't anything you can do if you don't know anything special about the matrices A and B. You cannot rearrange these things because, well, what you want to rearrange is exchange this A and B, their location, and you cannot do that because matrix multiplication is not commutative. So we have a few rules that looks like the stuff from high school, but also we have lost quite a bit. So we have to be always careful with respect to multiplication and such. Okay, let's go ahead and do a little bit of exercise on these things. So you have one set of exercises here, and then we are going to have in the next lecture, we are going to have a description, a more detailed description of process of inverse through the so-called elementary matrices. Take the mystery out of it, but perhaps add some extra mystery. Now we noticed that finding the inverse, it wasn't that painful really. For the 2 by 2 is not really that bad. Now what we might think is, well, let's have a quick recipe for a 2 by 2 matrix and have the inverse of that ready-made, even though the process when it goes to bigger matrices is just going to be painful anyway. So we are going to just take a look at a very special case, which is a case of 2 by 2. Is there a recipe for finding the inverse of 2 by 2? Well, the Gaussian operation we had up there, it can be applied in general, and out comes the following particular looking matrix. We get the following. We get these two entries exchange their place. This becomes D, this becomes A, and these two become negative of whatever they are at the beginning, so it becomes minus B minus C, and then all of these entries are going to be divided by a very special number, and that number is the product of these two AD minus product of these two, BC. The creature that you see here is going to be with us for the remainder of semester. That is going to be the determinant. So it's called the determinant. I write it with capital D. Your book writes it determinant. Determinant of a 2 by 2 matrix A, B, C, D is the product of entries on the diagonal minus the product of the other two is AD minus BC. It's only good for 2 by 2 matrices. Determinant is a very complicated function itself. We are going to talk about that later on. So what we have here is a division by determinant, and that is going to give us a clue as to when the inverse is going to exist. Of course, when determinant is 0, well, you cannot divide by 0 and the process is going to stop. So if you have condition if AD minus BC is anything other than 0, then the inverse of this is going to be that. Let's go back and practice with the problem we started at the beginning of this lecture. We had, what did we have here? 1, 2, 3, 4 something. Yes, 1, 2, 3, 4. We went through this process to find the inverse. Okay, here's a shortcut of it. 1 over 1 times 4 minus 2 times 3 times, exchange these two, make these two negative of what they are right now. Let's clean up. My denominator is minus 2. I have 4 minus 2 minus 3, 1. Multiplying a matrix by a number means multiplying each entry of that by that number. So I just do that. I divided everybody by minus 2. Let's clean up. So 4 divided by minus 2, that's of course, sorry, minus 2, this is just 1. This is going to be 3/2. This is going to, of course, be right the negative in front of the number. Minus 1/2. Let's remember, minus 2, 1, 3/2, minus 1/2, minus, where are we? Yes, here's our inverse, or here, minus 2, 1, 3/2, minus 1/2. That is the inverse. We found it by a shortcut. So shortcut only good for 2 by 2. You can make a shortcut for you can make a cut for 3 by 3 and 4 by 4, but it's not going to be short anymore. That's a problem with that. Is you can write it, but it's going to fill up a whole page and not all that useful. So in those cases, we just go to Gaussian elimination and do it that way, as opposed to try to struggle with the lengthy formula. So this one we are going to postpone it to later on. Determinant. You remember a long time ago I said the author of Alice in Wonderland has a contribution to concept of determinant. Interesting thing, you might want to read about it in your textbook. Okay, until next lecture, good luck and God bless.